Yeah, welcome everybody, and thank you, Matthias and team, for hosting such a great conference and such a great place. I hope you don't fall asleep in these cozy chairs. I will talk about transactions, and I started working in the financial industry some 15 years ago, and during this time I've seen different types of transactions, and yeah, I'm glad to give an introduction here. And if you have any questions, please just raise your hands, and because I really want to throw this microphone around. But we will do a quick Q&A at the end too. But if you have any questions, please just keep firing them. Okay, so no talk about transactions without specifying what a transaction actually is. And I think all of you have heard about these four letters, the asset properties. Who has heard about them? Yeah, I think everybody. But nevertheless, I will quickly explain each letter. The D is, I think, the most easy one. It stands for durable, and it means that if a transaction has committed, its effects doesn't suddenly disappear. You know? And this is, in my eyes, the easiest part, and we won't talk about durability anymore, except in one particular example where some people might have wanted a particular transaction to be durable, but unfortunately for them, it wasn't. So what's about the A, atomicity? So a transaction basically is a sequence of operations, read and write operations, that are either being executed completely or none at all. Yeah? And if you think about it in terms of reliability, this is actually a really great feature, but because if you are developing, for example, a container-based application, you have to be constantly aware of the fact that your application might crash or be evicted from the scheduler after every line of your code, and even in the middle of a line. Yeah? And you, as a software developer, you have to make sure that your application stays in a consistent state, even if your container is evicted at the worst possible moment. Yeah? And if you had transactional guarantees, you could take this for granted, yeah? That a sequence of transactions is either being executed completely or none at all. So what's about the C and the I? The C stands a little bit out here because it's formulated from the application perspective. And it means that if you have one transaction that takes a consistent state of your application, it leaves your application in a consistent state. And this is some kind of inductive argument, and it should be obvious, but in fact it isn't. Because to have these guarantees, you also need isolation guarantees, that you as a developer, you can rely on the illusion that every transaction that is executing in the system is alone in the sense that there's at most one transaction concurrently executing in the system. So a transaction is basically an abstraction for concurrency control. And let me give you an example. Suppose two people share a bank account, and you have 15 euros on this bank account. If one person is at an automatic teller machine and wants to withdraw 50 euros, and the other person is at the online banking and wants to transfer 50 euros to some other guy, and by circumstances it happens that these two transactions are concurrently executed in the system. And just suppose that the ATM transaction is a little bit earlier. Which transaction wins? Which transaction will commit? A little bit louder, please. The early one. Other opinions? Yeah. It's always the right answer, right? It depends, but actually this is true. The asset properties do not state anything about real-time guarantees. Yeah? So it is not guaranteed that the first transaction that enters the system will commit, because from a consistency viewpoint of your application, it doesn't really matter. The only thing that matters is that exactly one transaction commits successfully and the other aborts or is being rolled back. So you, as a developer, you don't care if the guy at the ATM or the other guy at the online banking can transfer his money, as long as your application stays in a consistent state. So if you think about this from a database viewpoint, it gets clear that the illusion that your transaction is the only transaction concurrently executing in the system is really expensive. Yeah? For example, suppose that you are starting a transaction and you are counting all your customers. And then you are doing some other stuff, and then you are counting your customers again. And what this illusion that your transaction is the only transaction executing at the system means in this example is that there cannot be a new customer or no customer can be deleted. Yeah? So the database has to make sure these things, yeah? And it's not obvious at all how a database should do this, because they can't lock a customer that not yet exists. And also from an historical perspective, I find it quite interesting the way the isolation levels evolved. Because nowadays, we don't only have this strongest isolation level called serializability, where you really have this illusion that your transaction is the only one being executed, because this is too expensive. We only have weaker isolation levels like read committed or even read uncommitted. And I have a question for you. What do you think did the historical development go? Did we start with quite weak isolation levels and evolve to stronger and stronger guarantees until we reached serializability? Or was it the other way around, that in the 70s or 80s, we already had serializability, and then for performance and scalability reasons, these isolation levels were softened up? Yeah? So to reformulate this question, did the applications over time always needed stronger consistency isolation guarantees or weaker isolation guarantees? What do you think? Hands up for stronger, for the development from weaker isolation levels to stronger? Okay, a few. And the other direction from stronger? Yeah, and this is correct. And this was, for me, really an interesting observation that even in the 70s or early 80s, the trade-off between consistency and performance and scalability already existed. Yeah? And the developers at that time really did make trade-offs where they sacrificed consistency guarantees to gain performance and scalability issues. But if we soften up the isolation level, we suddenly have to deal with anomalies. For example, non-repeatable reads, phantom reads, dirty reads, or lost updates. And in this talk, we will only talk about dirty reads, because dirty reads occur even if we try to restructure a large legacy monolith, and we take a kind of naive approach, but go into detail there later. So, what is a dirty read? Just to make sure everybody understands this. So suppose we have one transaction in the system, and we start with a balance of 0. Yeah? And then the transaction adds 10 to the balance. Yeah? So the balance afterwards is 10. And then again, the transaction adds 10 to the balance. Yeah? And at the end, the transaction successfully commits, and the balance is 20. So if any other transaction could have observed a balance of 10, this would have been a dirty read, because this is just intermediate state of this transaction. And it would also have been a dirty read if a transaction would have observed the balance of 20, but this transaction would not have committed, but would have instead been rolled back. Yeah? So this is a definition, or this is an example of a dirty read that we have to keep in mind for the rest of the talk. So the title of this talk is how to disentangle transactions in a legacy system. And I really have to apologize for this metaphor shortly before lunch, but I can't help but think of a kebab when I see some large legacy monoliths because, well, everything is just stuffed together without recognizable structures. But then, maybe it's your task as a software developer to restructure this monolith. Yeah? And I don't know if it's a thing in the Netherlands too, but in Germany we have a dish called a kebab plate, which is basically a well-structured kebab, but it costs much more. And I really don't get the point here. And okay, my personal opinion is of no interest, but I would really like to give you a recommendation that if you are responsible for a legacy restructuring process, you should always have a clear mission statement of why you are doing this restructuring. Yeah? Because what I have seen all too often is that the people have maybe 10 mediocre reasons of why they want to restructure this monolith, but 10 mediocre reasons do not add up to one compelling reason. Yeah? And you know how this goes, right? The people that are skeptical about your project, they pick the weakest argument, try to refute it, and thereby undermining your whole restructuring effort. Yeah? So please, if you are in a project that wants to restructure a large legacy monolith, please do have a mission statement because it helps your project from being prematurely canceled because the management doesn't understand the purpose. Okay, so back to the dirty reads. I want to give an example when they can happen. And for this example, I want to introduce a very easy legacy model. So suppose we have a customer, and the customer has an attribute daily limit, which basically says what amount of money he is allowed to transfer in a day. And then we have a second component, a payment processor that executes the payment. And also in the legacy system, we have teams, a team customer and a team payment. And as it happens, these teams work together for more than 30 years. And traditionally, the team customer owns the daily limit attribute and implements the check daily limit function and also the reduce limit function. And the team payment, well, they are responsible for the transfer money function. And in the legacy system, the corresponding code could look like this. And this is actually a valid COBOL. Yeah? We check if the remaining limit is sufficient, and if it is so, we transfer the money, and afterwards we reduce the limit. And here you have to keep in mind that you have in the legacy system transactional guarantees for this piece of code. So while this code is running, you are guaranteed that no other transaction is being executed. And if, for some reasons, your program crashes, all effects will be rolled back. So this is really a great abstraction for concurrency control. So, and now let's see what would happen if we take a naive approach and introduce a component payment manager that first checks the daily limit, then transfers the money, and afterwards reduces the limit. So let's make an example. The first transaction wants to transfer 100 euros, and the transaction starts, checks if the daily limit is sufficient. Okay, well, the daily limit is 100, and the check is successful. Then it transfers the money, but then the second transaction kicks in and checks if the daily limit is sufficient to transfer 20 euros. And this check is also valid because the limit has not been reduced yet. And then, the first transaction continues, the second transaction continues. But then when the second transaction wants to commit, we would have a consistency violation here because the daily limit would have been overspent. And this results from the fact that we do not have transactional guarantees between the calls to these components, right? Check daily limit, transfer money, and reduce limit. So what could you do? You could try to leverage the fact that one team, so let's just call it bounded context or aggregate or whatever, can have consistency guarantees, transactional guarantees in their component. So you might have a check and reduce daily limit function that is transactional, meaning that the asset properties are valid for this code. So what could happen here? The first transaction checks and reduces the limit. And then the second transaction kicks in. And now the check is rejected because the daily limit is 0. And it's not sufficient to transfer 20 euros. And the second transaction is aborted. But then the first transaction, for whatever reason, is aborted too. And if you think of the example from the beginning, we have two transactions where exactly one transaction should have been committed. And this is not the case here. Both transactions failed. And this is also a consistency violation. And this is actually a very serious problem, that when you restructure a monolith, you might easily lose the isolation guarantees. And there's a very famous paper, I think from 2017. It's called the Acid Rain paper. Put your hands up. Does anybody know this paper? Has anyone heard of the Bitcoin marketplace Flexcoin? Nobody? Well, this might be the case because they had a so-called scoping isolation violation that allowed attackers to withdraw Bitcoins in huge amounts. And in this paper, there's a detailed explanation. But basically, the reason was that the attackers could transfer Bitcoins between accounts, and the account balance was not always in sync with the real balance. So they went bankrupt because of such a missing isolation, right? And they also give other examples. What could happen if you get the isolation property wrong? For example, during a checkout process in e-commerce, items could be stolen, the store inventory could be corrupted, or gift cards could be overspent. And this leads me to the second recommendation, that if you want to restructure a monolith, you really have to watch out for business invariants that are buried under strong consistency guarantees. Because if you think about it, no business analyst would tell you that the daily limit should not be overspent, because this is just clear from the wording. But as a software developer, you have to be constantly aware of the fact that if you are restructuring code that was a transaction in the legacy system, might lose some of these valuable properties in the new system, right? And I don't want to sound overly dramatic, but if you get these isolation guarantees wrong, you might be responsible for an architecture that might possibly bankrupt your company, right? Just think of Flexcoin, and if you have some time, really check out this Acid Rain paper. It's really instructive. And the second tip in this context is that if you found a situation where these missing isolation guarantees might hurt you, and you notice that you are basically trying to implement isolation guarantees that you know from database systems, for example, locking or semantic locking, maybe you should go back to the modeling phase and say, okay, I've learned something. I've learned a consistency guarantee that should be respected. And yeah, try to remodel your architecture. And I'm fully aware that this is easier said than done, because in the example we saw with the customer and the daily limit, the actual problem or the error that the architect has made here was that the daily limit attribute should have moved to the payment processor team. Yeah? Then it could have been consistent, and you don't have to deal with these nasty anomalies. Yeah? But just to move one particular attribute from one team to another, you might also have to restructure the team, right? And it's not always the case that you, as a software architect, might have the power to do so, right? So this is, again, the situation. If you find yourself in a situation like this, where you want to restructure a team, because otherwise you might put the future of your company at risk, you should talk to your management. And if they tell you, stick with this architecture, well, everybody has to decide for himself what he or she is doing then. But for me, it would be like asking me if I would like to eat a dead rat. Actually, I wouldn't even think about it. No. Okay, so to wrap it up, the abstraction of a concurrency control. 5 years ago, in 2019, there was a serious security issue in Docker, which allowed containers to access the host file system. And if you think of managed cloud providers, for example, this is serious. Yeah? You don't want the containers of your customers to mess around with your host file system. And what was the problem here, and what does this have to do with transactions? So this C code here first checks if a user has access to a file. Yeah? So these are the first 3 lines. And if the user has access to this file, then the content of a buffer is written to this file. So this is easy, and what could possibly go wrong here? Well, it might be the case that in the time between the check of the permission and the use of the permission, an attacker is able to add a symlink from this file to another file and thereby overwriting this file. And okay, to completely understand this security issue, we have to make a distinction between real user ID and effective user ID. But for this talk, this is not important. For this talk, what is important is the isolation guarantee, or better said, the missing isolation guarantee, because you never have the guarantee that between the time when you check something on the file system, in this example, and the time you use something, nothing has changed in between, because you explicitly have not the guarantee that your transaction, that your piece of code is the only piece of code that is running in the system. Right? And if you think that this attack is unlikely because the attacker has to time his attack very, very well, to really add the symlink here in line 4, so to say, between the check and the execution, well, if you are a juicy target, you can be sure that even such vulnerabilities will be finally exploited. Okay, so up to now, I said a lot of the good parts of a transaction, but actually, with all good things, if they are used too excessively, there might arise problems. And I want to share a story with you. When I started working at a company fresh from university, I think it was one of my first issues that I was assigned. It was really a seemingly very, very easy issue, some kind of first committer issue. We had a legacy core system and some middleware before, And my task was to implement a check in the middleware because in one situation, the legacy system had a return structure, and in one field that should be non-negative, we sometimes saw negative values. And my task was to check if the value is negative, and if so, raise an exception. So, okay, I implemented this check, and a few months later, I got a really weird ticket where the CFO of a smaller company wanted to pay his employees. He wanted to transfer the salary. And he tried it, and he got a generic error message. And what do if you get a generic error message? You try it again. And so did the CFO. He tried it a second time, and he got the same error message, and he tried it a third time. Now he got a different error message, insufficient account balance. This was not ideal. And I was really puzzled. What went wrong here? But I think you can spot the issue, right? Because in the legacy core system, we actually do have transactional guarantees. And the transaction that transferred the money to the employees committed successfully and returned to the middleware. Then my glorious check kicked in and raised an exception. And this was not ideal, to say the least. But actually, this was a great learning opportunity for me. But what it tells you is a bit like what good transactions should look like. They should be deep in the sense of spanning the whole way from user to database. But they should also be narrow in the sense that on the legacy system, the transaction should ideally not span components that belong to multiple teams, because this is really a burden to restructuring efforts. And what also is really a big challenge in these kinds of architectures is when you try to integrate services that are not supported by your transactional monitor. For example, if you want to call a REST service, how would you do this? You just can't call a REST service in a transaction. What should happen if the transaction is being rolled back? This is really difficult. Okay, so no talk about transactions without mentioning 2PC, two-phase commit. But I will promise to keep it short. If you find yourself in a situation where you do not have transactional guarantees, you might be tempted to go for two-phase commit. And two-phase commit basically works like this. You have an orchestrator that asks in the first round every participant if the participant is ready to commit a transaction. And if all participants agree, in the second round, every participant gets a notification to actually commit the transaction. And it's really, really important to keep in mind that two-phase commit only deals with the A in asset. It only deals with atomicity. It makes no assumptions about isolation, for example. And this is easy to see because in the second phase, where the orchestrator gives the command to commit, maybe one participant commits earlier as another, and in this, even if it's only a short period of time, you can observe dirty reads. And these dirty reads are really sometimes a really serious issue, as we have seen. And there are two other problems that I want to point out with two-phase commit here. The first one is, like in the beginning, if you are developing a container-based architecture, the orchestrator in a two-phase commit setting is inherently stateful, because the orchestrator has to always know the exact state every participant is in. And if you always have to be aware of your container being evicted or crash, this is not so easy. There are products out there that address this specific issue, but I just want to talk about concepts and not about products. And the other problem is that if you think about the question, which team should own the orchestrator, team A or team B? It's not obvious at all, because the orchestrator needs to have knowledge about both A and B, right? The orchestrator needs to know how to handle the failures of A and B. And so this is a common problem. Which team is responsible for the orchestrator here? Okay, so the talk is titled How to Disentangle Transactions. And suppose we have a large legacy monolith, and we have a large transaction that spans multiple databases or multiple tables in a database and multiple components in a system. What I find really helpful here is the concept of a business transaction compared to a system transaction. And this is a concept Martin Fowler introduced in his book, Patterns of Enterprise Applications Integrations, I think more than 20 years ago. And a business transaction, I think all of you know what this should mean. You can call it workflow or long-running transaction. This could take a business transaction could actually take many years. Yeah? If you think of a process of a medicine, pharmaceutical medicine, or it's really a very short workflow. But the point here is that to disentangle this large transaction, it really helps to identify the system transaction. And with system transaction, we mean these kinds of transactions that we've spoken about earlier, these asset sequence of operations, sequence of operations with asset guarantees. Yeah, this is a system transaction. And if you can find the boundaries of multiple system transactions in one large business transaction, this should really guide you the way of how you can disentangle this transaction. Yeah. Okay. And yeah, this is the last tip that to find really these boundaries of the system transaction, you should look out for consistency boundaries in your system. Yeah. And another very, very interesting aspect are these so-called read-only transactions, transactions that do not modify state, but actually only read state. And it might be obvious that these are very easy, but in fact, this is not as easy as it might sound. For example, suppose you have a payment manager, again, who calls the get remaining daily limit function, and in this case, get all payments of today. Yeah? So you want to show your customer his remaining daily limit in all transactions of today. What could happen here is that during the time when you read the daily limit and the second call, yeah, where you collect all the payments, a new payment would have occurred and the daily limit has changed, right? So it's not obvious at all how to really ensure that you show your customer a consistent state here. Yeah? And the point is that even in a legacy system where you have transactional guarantees, you cannot easily guarantee this. Yeah? If you think about it, if you're selecting rows from one table and afterwards you're selecting rows from another table, you have absolutely no guarantee that in the meantime, between these two selects, nothing has changed. Yeah? And in fact, things do change, and you have to deal with these inconsistencies. But here, it really depends on the database system you're using. If you have something called snapshot isolation, this might be really come to handy here. But yeah, it's really dependent on your database system. And here we have to deal with staleness, right? Because this is actually what's happening here. Yeah? In the moment when you do the second select, the information from the first select might already be stale. And I really like the survey of consistency models from a website called Jepsen.io. I really recommend to check this out because it's really instructive. On the left-hand side, we have the isolation guarantees that we've spoken about earlier. But on the right-hand side, we have something that is called a freshness guarantees or recentness guarantees of data. Yeah? So suppose you have a distributed system with multiple copies of your data, and you want to make sure that you always get the latest state. Yeah? So-called one copy semantics. Then we would be here in the strongest consistency guarantee, linearizability, right? And actually, who knows the CAP theorem? Yeah, a few. The C in CAP theorem also means consistency, but consistency in the CAP theorem actually means linearizable, right? So it's really confusing. But yeah, there's a parallel talk about naming, and yeah, this always gets in the way. And I want to show you why these freshness guarantees of data also lead to safety violations by explaining to you I think it's the most severe safety violation in Kubernetes that is not fixed until today, but is known since more than 6 years. So the basic setup of Kubernetes is actually like this. Yeah, we have a etcd cluster here, yeah, and we have some API servers that communicate with the etcd cluster. And every call from the API server to the etcd cluster is linearizable, meaning that they always get the latest state. No stale data is allowed. Yeah? And where could be the problem with this architecture? Who can spot a problem here? Okay, I have to apologize. This is kind of a trick question because the problem is not visible here, but as in the beginning, these calls do not scale. They are much too slow and too expensive. If you think of Kubernetes clusters that have more than 100,000 pods, for example, yeah, and one call from the API server to etcd is, for example, give me all the pods that are currently running in this cluster. Yeah? So the etcd cluster has to do a consensus algorithm, marshal the whole list of pods to protobuf, send it over the wire, and the API server has to deserialize it. So this is really expensive. And what do you do in such cases? You introduce a cache. Yeah? So why is this a problem? Yeah? And the problem, the problem arises when we have a network partition. Yeah? For example, we have here on the right-hand side an API server that is disconnected from the etcd cluster, but it doesn't notice that it is disconnected. Yeah? And the cache is stale. Yeah? And now it could be the situation that a rolling update occurs. This kubelet shuts down a pod, yeah? And Kubernetes schedules this pod on another kubelet. Yeah? But then, because we have a staleness issue here, yeah, this kubelet does not notice that this pod has already been scheduled on another kubelet. And so this kubelet schedules this pod again. And so we have the situation where we have a Kubernetes cluster with two pods of the same name concurrently running. And if you think of stateful sets, for example, this could lead to corrupt data when you have multiple processors accessing data in a non-coordinated way. And this is really not ideal. So again, here in Kubernetes, we have an example of a trade-off between performance and safety, right? And this is also the reason why this issue isn't fixed for more than 6 years. Yeah. So maybe one reason is that it only happens on really, really big clusters. Yeah. And also there is no easy fix, right? This is an example for a CAP theorem in the wild. Yeah. And of course, just removing the cache here is also not an option. Okay, so that's basically it. Just a summary. I won't reiterate it because if you want, you can take a photo. I think I've said everything to these points. And then, yeah, we have 8 minutes left. If there are any questions, I really want to throw this mic around. Yes?
Hello. Yeah. You mentioned it's useful to think in terms of business transactions and system transactions to figure out what system transactions and business transaction is composed of, but the business transaction is still supposed to be a transaction, right? But we don't have these isolation guarantees for it. So what then? I guess we know now that this business transaction is composed of multiple system transactions, but what do we do with that knowledge?
Actually, I don't think that a business transaction really does need to have asset properties. So if this would be the case, that you have examined really, really carefully that the whole business transaction needs asset guarantees, then it would be a system transaction, right? But usually, this is not the case. You always find steps in your workflow where it's okay to be not atomic, or where dirty reads might be acceptable. So if your analysis shows you really need to have asset guarantees for this sequence of code, yeah, then it's the definition of a system transaction.
Thanks. You were talking about disentangling the transactions. Do you mean that we need to create, for example, distributed transaction with a smaller transaction in microservices? Or no, we redefine our domain to have smaller transactions that they are meaningful standalone?
Yeah, that's actually a good question. At least for me, it was surprising that if you are talking about distributed transactions, if you are developing a distributed system, you actually do not have to give up on asset guarantees. You can have asset transactions in a distributed system. This is actually not a problem at all. But what you might have to deal with is stale data. So here in this consistency model survey, this side of the graph is maybe more problematic in a distributed system than the isolation part on the right, on the left-hand side. There are products out there that guarantee you asset properties for your transaction. There are lots of databases. And actually, Here again, the historical development is quite interesting because when NoSQL databases were first introduced, I think about 2005 or 7, they did not provide transactional guarantees at all. Yeah? But in the last 4 or 5 years or so, we can see that they, for DynamoDB, for example, actually do add transaction support because it's really, really difficult to ensure a consistent state of your application without transactional guarantees, right? And also here in the Kubernetes example here, the cache is introduced only for read operations. The write operations from the API servers to the etcd cluster always have asset guarantees. And the strongest possible asset guarantees with isolation level serializable. Could you throw the mic? It's the right receiver.
Thanks. Going back to one of your earlier slides you had there, which was the orchestrator. One of the situations, actually, I see this and there's a bit of familiarity, which is we've actually become the orchestrator team in some sense. So it's like these teams that are A and B, what would you feel is like the best way to kind of like bring these type of people on board and realize that they are part of that business process?
Yeah, maybe, but it really depends on your culture, on your company culture. Some kind of inner source, if really team A and team B could be responsible for the orchestrator together. Maybe you have some framework in your company.
So that is kind of what I'm also looking at, is we've realized we've built a bit of a GitOps platform that people can come to. But I guess it's like, you know, if you build it, will they come? Hopefully. Yeah.
I think you should have a framework, some kind of product that ensures the statefulness of the orchestrator. But yeah, whatever product you choose. But then the question you said, right, which team is responsible for the content of the orchestrator? And yeah, maybe your company is mature enough to have some collaboration between team A and team B there. I don't know. Microphone coming from behind.
This way, thank you. Now, thinking about it, does it mean that we are actually back to square one where the boundaries and the flow was poorly identified? To me, the situation when we have to do this that way means, are we really in a well-designed system? Because to me, it means that it is supposed to be a workflow. And for that, it's just an implementation detail, whether you use orchestration or choreography, and you don't need to delve into that ownership because you should have isolation on the design level that it doesn't really matter. They cannot break their own, nothing beyond their contract, so it should be fine. So why do we need to think about orchestrator and extracting teams, managing teams A and B? It's just a part of the contract that you are here and that's what you do. Otherwise, we're always going to have that problems no matter how mature the organization is.
I'm actually not sure if you can solve the isolation issue at the design level. If you think about the example with the daily limit, there's actually no way to soften these guarantees there. Yeah? It's forbidden to overspend the daily limit, but you can also not, the other way, deny people some money that they are actually entitled to spend. Right? So if you do not have strong isolation guarantees, you find yourself in one of these two situations, overspending or denying them money they actually have. And if you're in a situation where both of these alternatives are not valid solutions, I think you have to go for transactions here with most strong isolation guarantees. But this highly depends on the domain you are working in.
Okay, I take it as you said it. To me, it still sounds like that's a scope of a system transaction, and therefore the initial division to multiple teams is inherently broken.
Yes.
Period.
Yes. And maybe the reason, therefore, is that in a legacy system, you 20 or 30 years ago, you didn't need to think about, do you need a transaction or not? You just had a transaction. It was easy to use, yeah? And with like all the good things, yeah, if it's easy to use, then they are overused. And maybe it's your job as a software architect, yeah, to pay these, yeah, social, technical debts, however you would call it back.